Hey everybody, this is Larry. This is me doing week 3 of the weekly premium problem or whatever it's called. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's premium or this week's premium problem. Today's premium problem is 1066 Campus Bikes 2. On a campus restricted or represented by a 2D grid, there are N workers and M bikes, where there are more bikes than workers, and they're on a grid. We assign one unique bike to worker so that sum of the Manhattan distance between each worker and their assigned bikes is minimized. We turn the minimum possible sum of the Manhattan distance between each worker and their assigned bikes. I am curious about some parts of this for sure. Manhattan distance does make things interesting. And the first thing that okay, fine. I was wondering whether what the constraints were, and the short answer here is that the constraints are 10. This is actually going to be a brute force, like a 10 factorial, but you save it so that it becomes 2 to the 10 times 10 instead. So basically it's a bit mask dynamic programming problem. But of course, this is actually also you can also solve this with min cost max flow or the Hungarian. And given that n or m or whichever is less than 10, you can use either or both really. But these are things that, of course, I know that I said a lot of kind of fancy terms, and definitely maybe Google did update city min cost max flow, and this is kind of min cost by paradigm matching. Did I spell that right? Matching. Maybe I misspelled this one. Let me see. Because I can't spell today, and Google is slow right now because I need it to be fast, of course. But anyway, spelling aside, that's one thing to Google on. Another thing is go to Hungarian algorithm for matching. There's no A, huh? What am I thinking of? But yeah, bipart matching. So those are things there. But the way that we're actually going to do it is bitmask dynamic programming, which is kind of I don't know if I'm a fan of that term. The way that I think about it is more, what's it called? Like 2 to the n dynamic programming maybe. And the idea here is just basically brute force every possible worker in the bike, right? So basically, let's start our recursive function. And again, this is a dynamic programming week, but I'm going to go over it really quick, and really, I'm going to go over bitmask very quickly. So the way that we may naively write this recursion is just, so for each worker, we put it with a bike, right? So let's do, let's just write assign maybe, and then, maybe an index on the worker, and then bikes left, right? Or bikes free maybe? Let's say bike used, right? And another way to write this may be that bike used is a set, right? So maybe you can assume that bikes used is equal to a set. And maybe another way of, instead of writing a set, is that that this has 10 elements, right? So maybe another way to optimize that is just writing is equal to force times 10, right? Or whatever the number is. Let's just say W is equal to length of workers and B is equal to length of bikes, right? So this would be number 4 is equal to B. But of course, what does this represent, right? Meaning that you can kind of, if you stretch out what it looks like, it will have something like FF, whatever, right? 10 of these or whatever. And sometimes you flip them to be true as you go on, right? To see if they're used, right? So that's basically how you would write it. Say if you do a backtracking, maybe you have a bike used as equal to an array of 10 elements or B elements, and then you just flip on and off as you go recursion, right? So this is basically that idea, is that with bitmask, it's just that we converted this number, or this spoiler alert, this array of true false values to zeros and ones, right? And once we convert it to zeros and ones, then now you can just be like, okay, well, if we convert it to ones and zeros, then this is just a binary number, right? Meaning this is base 2, but 0 index, 1 index, dot. So this is a 4, this is a 16, dot, right? And this gives you a number. So that's I know that people kind of make bit masks out to be this really scary thing, and I wish that this video was in premium, so that people could see it more. But yeah, but that's really all there is for bit mask dynamic programming. Yeah, maybe I'll recut this for another tutorial or something. But yeah, but that's all bit mask is. It sounds scary. You have numbers and people do operations in a weird way, but that's all it really is, right? Because there are a couple of operations that you need to do, and it just that they get represented in a funky way. The for example, the two operation that you may do is like if bikes of used of I don't know 5 is equal to true. I mean, you wouldn't write out equal to true, but you get the idea. And then it's just the same as well checking if this bit is a 1. And of course, you have to write it in a funky way, which I'll show you in a second. And then the other thing that you might have to do is, set bike used of some index is equal to true. So this is assignment, right? And of course, this is just equal to this flipping, say the third bit or something like that. And of course, that's an OR operation. And again, that the function looks funky. I'll write it out then. Huh? Greater than 0, and you have to be careful about parent, right? So you have these things, and yeah, they look funky, but really, that's all that. And it looks intimidating to be like to see this and like, oh, what is this going on, right? But really, that's all these translates to, and that's all these translates to. So that's all bit masks are. So yeah, okay. So with all that written, let's write the code, right? So if index is greater than or equal to W, then we've done everything. So then, what are we trying to minimize it? Yeah. So then we return 0 because we've done. Otherwise, then now, so current worker xy is equal to, or let's just say wx wy for is equal to worker of index, right? And then now we just go over for b index for bike index. So I suppose in range of b, right? And then now again, so we use this, right? So we would have maybe, well, if bike used of b index is equal to true. I mean, again, you wouldn't write it quite like that anyway, but I'm just illustrating. So instead of writing that, we write oops. What is it? B index, right? So if this is greater than 0, then this is true. That means that there's a 1 bit there. Then let's try to use it, right? So I forgot to optimize. So we want to minimize the cost. So cost, let's just say it's some infinity value, right? Let's double check the constraints. 1,000, so it should be good enough, so that we don't, choose a too small infinity. So then now we're like, okay, let's use this. So then cost is equal to min of cost assign index plus 1 because we moved the worker along, and bikes used or 1 b index. Again, this is just setting the b index to true, except what we did in one statement. As we did the recursion, and then we add the cost of assigning the current index to the b index, which is the Manhattan distance. And you could probably pre-cache this, but I'm just going to write it out anyway. So what is this again? Let's just write it out. Let's just write this as c. So c is equal to, or bx by is equal to bikes of b index, and then c is just equal to wx minus bx, absolute value of that, plus absolute value of this stuff, right? And then at the end we return cost, right? And that's pretty much it. So we 0 and 0 because 0 just means that everything is false. So yeah, again, this is going to time out because we did I mess this up? No, it seems okay. I'm returning the right thing. Now why are you giving me issues? Am I using a weird language or something? I am in Python, right? So, what is going on? I know that maybe I returned infinity by accident, but oh, I messed up here. because you wouldn't write this as equal to true, you write this as equal to false, so this has to be 0. But still, I didn't know that that's a thing. So I messed this up here in the explanation. Sorry, friends. But yeah, not sure why this is wrong though. Is it just returning 0 for everything? Cost is equal to this. Did I mess this up? Oh, I put the C inside, that's why. Okay, so that's why there was a lot of funky things going on. Okay, so like I said, man, it's hard to tell sometimes, huh? But yeah, as you can see, everything is a-okay. Except for the caching, and it'll time out, probably. May not, I mean, it's 10 factorial, which is what? Like 86,400 or whatever it is, or 8 million? I don't remember which one it is. So yeah, but in any case, so we just have to do caching is basically what I was going to say. And yeah, so what does index goes from, right? Index goes from 0 to W, and what does bytes used go from in this case, right? It goes from 0 to 2 to the B minus 1 inclusive. So yeah, because that's all the possibilities of the zeros and ones, and so let's cache it that way. So it has cache is equal to force times always forget to this auto thing is more annoying than me typing it out manually, but yeah. And then now, of course, let's reset. If it has cache, and the part about dynamic programming or memorization, I actually said it like in the other video that I did today. So it's kind of tricky for me to I don't know. Like I feel like I'm saying exactly the same thing, but yeah, if you get the same input and you get the same input for every same output, that's basically when you would want a dynamic program, or you want to do memorization. Looks good, 989 days streak, and actually pretty fast relatively. What is complexity here, right? Well, the complexity, as I always say, as I always try to explain it in this way, because I think people have trouble going over the complexity sometimes. So total number of inputs is equal to O of W times 2 to the B, right? And each input takes O of B time, because this is the B here, because you have a for loop of B. So total time is O of W times 2 to the B times B, right? And total space is O of W times 2 to the B, because each input takes O of 1 space. That's pretty much it, really. That's all I have with this one. Let me delete this so you could see maybe more of this in one. Yeah, okay. So you kind of see all the code in one thing. Let me know what you think. And that's all I have for this week's premium dynamic programming problem. Yeah, stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye-bye.